This conference will now be recorded.
Want to cover today before we get things off? We have our young engineer bit coming up, which is a trivia, and there's a little bit of a challenge on the table, and it's the young engineer against the young at heart.
Hey, how long are we supposed to go for?
Somehow they define young
I would like to talk for
engineers
hours, you know.
I mean, I'd probably gauge it like we did the other one.
I didn't really gauge it.
There's not a whole lot of young at heart who jumps the
What happened to my watch? Holy crap, scraping my watch up. Yeah, maybe,
25 minutes again?
yeah.
50 minutes?
Yeah.
building engineer for all of ConocoPhillips North Star assets. And before that, he was design build mechanical contractor. He's also a past president of our local Ashrae chapter, and he's our current
It's all right.
chair.
She's giving me a bunch of my stuff.
It's on the cold climate design guy tech.
We were really fast. Anyway, so I think I'll talk for about 20, 25 minutes, and the Mac will probably be the same. So if it gets long, give me the high sign. And I spent my time with PDC, and back then it was FPE Rowan, and I was there. Yeah, let's get on with that. Yeah, that was the Ashrae conference. Yeah, they're like, you can't start without that. So anyways, okay. But first of all, so this is an oil and gas presentation. And the first thing at any oil and gas meeting you do is a safety moment. So what I want us to talk about first is Deepwater Horizon, which 10 years ago in April, it doesn't really work. All right, so 10 years ago in April, Deepwater Horizon, BP a well was being drilled on BP's behalf, and at a blowout, major incident. I'm sure most people remember, or if you don't, it's in, you can go on the web and find out the cause and all this, and they made a movie and whatever. But the thing that's most important, 11 people died. And so what Mac and I are going to talk about today is so that part of it is so that another 11 people don't die.
Eight things were breached, 8 barriers. Hardware. And one of them, breach number 7, and it was fire and gas didn't prevent the hydrocarbon ignition. And they talk about operation of gas dampers. Oh, boy, that's HVAC stuff. And so one of the quotes they had out of it was the HVAC system probably transferred a gas-rich mixture into the engine rooms, causing at least one engine overspeed, creating a potential source of ignition. So electrical area classifications, safe areas, we're going to talk about this here in a little bit, but you have safe areas and hazardous areas, and gas went from the hazardous area into the unclassified area where you have arcing and sparking of equipment, and explosion, bad stuff. So one of the things that talked about, there was a gas dispersion analysis. So the wellhead Now here's the derrick there. The gas flow is here's the lower explosive limit and upper explosive limits. You can see the whole platform is engulfed. Here's the living quarters and the heli deck. So that's incident. Gas is spread everywhere, and when it's beyond the electrically classified areas, ingress in the engine rooms. And the thing I want to point out is HVAC is a protective system. So it's not just indoor air quality and am I cool or am I hot. On oil and gas applications, HVAC is to protect us. It's a secondary protective system. You know, there's pressure relief valves and whatever that are also included there. But the point I want to bring out is it's a protective system. All right, so let's move on. Okay, so, and we gave this presentation in Orlando. Everybody here knows what oil and gas facilities are, but there's a lot of people in Orlando who have no clue what we're talking about. So bear with us. What are oil and gas facilities? Well houses, piping, gathering centers, metering modules. And I also do want to say, so this is cold climate. I'm going to talk in more general terms around oil and gas and codes and such. Matt's going to take this and go a little deeper into more application. So oil and gas facilities, we have offshore platforms, we have tankers, we have FPSOs, we have all sorts of stuff. Okay, cold climate's enclosed. What are the main focuses on main focus of these facilities? Continuous operation, can't stop 24/7. Isolated, of course, look, great example, but we also get to offshore places or Tanggu, Jakarta, weird places. They're hard to get to. Isolated, remote. Utilize sparing and redundant equipment. There's a lot of N+1 duty standby equipment. Very common. You can't get it. You gotta have backup. And kind of the kicker is limited HVAC supports. You get these great systems, but no one's an HVAC guy. It's an electrical guy working on it or somebody else. All right, HVAC considered support utility, influenced by process design and process safety. So in the world of oil and gas, those guys are key. So the process engineer will say, this is what my gas process will look like. And process safety says, here's my hazards are. HVAC then comes back and puts in equipment as a protective system to mitigate some of these hazards. Oil and gas standards. So I came out of a commercial building background like most people did. This is a little higher standard, a little more attention to detail, deliverables. It's when you're remote, you have to have conducting an instrumentation drawing DNIDs that are exact, accurate, that really show a lot of detail. There's a lot of scrutiny on deliverables. And then recent focus on greenhouse gas emissions. That's the new buzzword around here. The full challenge. How do we get more energy and less carbon greenhouse gas? All right, so a couple photos. Well house somewhere in Kampen and a couple other interesting things. All right, hazards and philosophy. Oil and gas hazards, what are they? Flammable toxic gas release. You got unplanned releases, not worth thinking about. You get your fugitive emissions, which always occur. Flange on a valve, a stem on a valve, always fugitive emissions. So fire events, blast events, asphyxiants. We got enclosed modules, and we have nitrogen that were, that are asphyxiants. You have acute and long-term effects of exposure. Guys who are running pigging operations, they're getting blasted with hydrocarbons every time they open it up. Extreme ambient conditions, noise. Don't often think about noise, but really loud processes, people go deaf. So something to be aware of. And then what is oil and gas HVAC's main function? Well, number one, mitigate the hazards associated with the hydrocarbons. And number two, maintain the indoor environment so that operations, continue. So our sprinklers don't freeze, and the equipment doesn't fail. Way down here at number three is maintain occupant comfort. And indoor air quality. A little backwards from the building industry perhaps, where indoor air quality is at the top. Safety is paramount. All right, codes and standards. So at the top of the house, you have the normal HVAC stuff, IMC, IBC, Ashrae, SMAC, whatever. And then in Alaska here, probably most people know this, but we have our local code revision, the IBC Annex LL oil and gas facilities. I will say Alaska is one of the few places, not the only place, that has this. I've not run across this anywhere else. Run across U.S. Coast Guard and OSHA, CFR type stuff, but something specific for oil and gas is very unique to Alaska. All right, so then on the oil and gas side, what are some of the codes? Our API, American Petroleum Institute, API RP 500. RP stands for Recommended Practice. Not a code, it's a recommended practice. API RP 500 and 505 are almost the same. They're electrical area for classification. The difference being Div 1 and 2, Zone 0, 1 and 2. Div 1 and 2, as it's referred to, that's mostly in the US. You can kind of broadly say that. And then Zone 505, it's a little more European in application. But you can use those either place, and that would be during the code setting phase of your project, they would identify that. And then NFPA has to get in on the game, and they have 497, which is their classification of areas for electrical installations. And that's basically talking about, those three are talking about if we have a hazard process, well, I got a good example here. I'll come back to that. All right, more codes. API RP 505 Annex B talks about fugitive emissions. So these are 4589, 4638. Those are two good guides for how to calculate the fugitive emissions. NFPA 496, that's the big one that if you're doing HVAC, oil and gas, that's the big one you're going to worry about. That's the pressurized enclosures for electrical equipment. Pressurization of control rooms, electrical rooms. Yeah, type X, Y, and Z pressurization. That's a big one. Okay. Other examples where codes and standards are different. Building services, B319 gets used. I don't know if we use it often, but that's one we would use. But in oil and gas, everything's B313. So you got to be aware of if you have glycol piping for a heating coil, you're probably going to mate up to a different type of flange. You got spec breaks you got to deal with. On the international side, you have these are just some examples. EI 15, Energy Institute 15 is the international equivalent to API 500. IE 60079-13 is the equivalent to NFPA 496. And then Chartered Institute of Building Services Engineers, CIBSE. That is the UK version of Ashrae. And there's a lot of collaboration, starting to be collaboration between the two. But when you do a design and you're international, like here we'll say follow Ashrae standards. Well, internationally you say follow CIBSE standards, or follow CIBSE or Ashrae. It's very equivalent. And then Heating Ventilation Contractors Association, which actually is, they've changed their name, but they have a guide, DW144, and that basically equals SMACNA. Whatever SMACNA is, they're the same thing, but it's the other side of the pond, as they say. ISO standards, and then IOGP, which is International Oil and Gas Producers. Joint Industry Practice 33 is where all the big guys are Total, Exxon, well, not Exxon, Total, Chevron, Conoco, BP, Petrobras. They're all trying to get together, not just for HVAC, but to create common industry specs. So if they want to buy a pump, buyers know what to give them. So they're actually trying to make what I think is just CSI specs, really. Everyone's got their own custom spec. But anyways. All right. Offshore stuff, IMO, International Maritime Organization, SOLAS, Certified Authority. We run into that a little bit on onshore, if you start to get into these really crazy fire dampers, high rated jet fire, long duration, you get into that, but we really don't onshore get into that too much. ISO 15138 is a really good guide for offshore HVAC. It's pretty good. All right. Okay, now electrical area classification. So we talked about API 500, and the differences are Div 1 says gas is expected to exist during normal operation. So if this is an example, and here's our gas source, this would be like a Div 1 boundary. Div 2, gas may be present, so it's a bigger boundary. And then the 505 is different in that zone 0, they're saying gas is always present. So they just classify it a little differently. Zone 1, gas likely to exist. Zone 2, gas not likely to exist. I'm not exactly sure why there's the two differences. I mean, the two div and zone documents, but there are. All right, so if we have this gas boundaries, hazardous area, things go boom. We have a control room, arcing and sparking equipment. We want to protect that, so then we put in a vapor tight barrier, and we can say, oh, we're isolated. Don't. We have to extend, because this is an enclosed module. We have to extend the boundary, the hazardous area into that module, which is what we don't want to do.
That causes you to have to buy a whole bunch of really expensive explosion-proof or intrinsically safe electrical equipment.
Yeah, there's stuff that you can't even get it for. And if you got questions as I'm talking, I mean, just shout them out, raise your hand, whatever. Okay, so that was kind of the generic. Now this is a real life example. So we have a process module here with something going on, and we call this Div 1 area. And we have a couple doors, and I'm guessing there's a door here, and there's a vent over here. So the boundary then extends, the API 500 and 505 give guidance on if you got a hazard in this module, like how far does this bubble, this hazardous area go? And this isn't an HVAC, this is not an HVAC job to determine. This is where your process safety guy comes in. So the process guy says, it's gonna look like this. Process safety guy says, what are the hatch, here's your Div 1, Div 2 boundaries. HVAC guys get involved for guidance, it's usually between the process safety, and electrical guys. All right, so you got the process, you got a control room here, an electrical control room. In this example, we have a vapor tight barrier that protects us. And we have this hazardous area here, so we have a cooling load in here. So we can't pull our intake from this side, we got to pull our intake from the top. So your air has to obviously it has to come from a non-hazardous area. A couple interesting things. Vapor tight barrier. Doesn't the code, the NFPA 496 and APA 500, they don't say what that is. They just say vapor tight barrier. So it's a little bit debatable. There's been some practices where you put a 6-inch gap between the building and that's considered safe. There's been practices where you use like a sheet steel welded. Practices where you use like a tie-back, something, and it's a little bit of gray space. All right, adequate and pressure ventilation from clean air source. Yeah, we talked about that. All right. Okay. Adequate ventilation. What is adequate ventilation? The term gets used a lot. I probably have already said here. Adequate ventilation by API 500, 505 is ventilation sufficient to prevent accumulation gas-air mixtures up 25% of the LEL. That's what we kind of hold on to when we do analysis. We say LEL is, I don't quite remember the numbers up. I can't remember, 4%, 15%, doesn't matter. We have your process safety guys. That's the process.
Methane. LEL is your lower explosive limit.
Yeah. Okay. Lower explosive limit. Interchangeable with LFL, which is lower flammable limit. They're not quite the same, but they're used interchangeably. So adequate ventilation, the API 500, 505, they say provide this. Many documents will talk about that. And you're like, what is adequate ventilation? Well, luckily enough, there's two different ways you look at this. One is in each of the different governance codes, they give us a nice prescriptive amount. So that's really cool. So we can look at API, RPI 500, RP 500, we got mechanical ventilation, we got to use 6 air changes an hour, whatever. We've got AMC, 1 CFM square foot. Yes.
Already 12 air changes an hour, natural ventilation.
How?
Yeah, what's causing it to?
So there's a couple different ways you look at it. One has to do with temperature-induced ventilation, and then the other is just ambient wind. And there's a couple calculations in back of 505, I think it is, and it'll talk about how big your openings have to be with respect to temperature gradients, and then wind, which percentage of the time. You know, you look at the max wind. I think they give guidance on the percentage of that you can take. Guidance in there. I will say more slope, you have to do that. It's like lower 48 gas fields where you have compressors that are enclosed for residents don't like what they look like. Gas compression, countryside of Colorado. Close. A lot of natural ventilation there. But what I want to point out is that we got these codes and we got the numbers. But if all of a sudden you got to do IMC and you got to do RPI 500, they might contradict and they might not get the same values. So you got to be careful with what how you're applying those. And you may say, you know, there's a couple, they don't all add up. And so it's a gray space where you have to do some engineering judgment. And I can't really attribute what the differences are, what stems them, other than some of these are European, some are US, onshore, offshore, just different areas. But what they do say, also, they all have a little guidance note. But the guidance note said, adequate ventilation, you can consider having adequate ventilation if you do 6 air changes an hour, but you don't really know it. But then there's another method where you can look at what are my gas sources, what's the emission, and you can look at it from an analysis standpoint. I really need this many air changes an hour. And I'll say in the oil and gas world, everybody talks about air changes an hour, not CFM a square foot. It's a little bit different. Like it or not, that is what everyone talks about. How many air changes? And from an owner's perspective, we get nervous when someone says, oh, I've done a calculation, here it is. Because now you're relying on quality of that calculation and the assumptions made. And it's just, you know, for all smart guys, like everyone in this room, guys and gals, fine, we're great. But when you deal with other people, other countries, or other skill sets, it's not always that great. So anyway, next slide. All right, how do we determine it? How do we determine ventilation? Right, so just normal HVAC stuff. We look at our prescribed adequate ventilation, we're calculated. And then we look at cooling loads. You know, we may have adequate ventilation of 6 air change an hour, but the cooling load of the module requires 12. Covered. Another piece, adequate ventilation. The coolest thing about it that you do, it can reduce our electrical area classification, the hash marks, from Div 1 to Div 2. And electrical equipment in the Div 1 is expensive, so it means gas is there. It's got to be built tight, have flange, have the right gaskets, got to have the right regulatory listings, yada yada. It's expensive. So you can save cost, reduction in complexity. So it's in everyone's best interest, and I would think most modules we run into, you're going to have a reduction from Div 1 to Div 2. But the electrical guys, their emergency lighting, their egress, they make it all Div 1. They have to pretend it's space. So you'll run into this. There will be some Div 1 equipment in a Div 2 space. All right. Recirculation of air. So we talked about 6 air changes. In order to high heat cave, we need 9 air changes an hour. But if you take that outside air, as we all know in the Arctic, that's really expensive. So you're allowed to recirculate, but there's some caveats. You have to kind of monitor the space continuously with gas detection, and then upon a release, you have to have the capability to go to outside air. This is the piece, the alternatives to adequate ventilation. Do that. Get your process safety engineer involved. It can be done, and there's times to do it. All right, next topic. All right. Okay, operating mode. So we do design, and one of the differing things. So different modes. You got a normal mode. We operate normally. You got an emergency mode where a plant upset, something happened. Shutdown mode. Okay, we're planning to shut down, but we got to shut down nicely, or else things bad can happen. A purge mode, where you would say either for a gas event or smoke from a fire, we're going to purge the space. You got these different modes, very common in our industry. You know, we think about the different modes of operation. But you'll be shocked at how many people do not. They just think, oh, what's the flow rate? What's static condition? Okay, a couple interesting things. This is a pigging module. Outline the pigging module. This is the air handling unit that goes like half the volume is air handling unit. And this is actually an offshore application. This is all the kitchen exhaust. Kitchen supply air, redundant equipment, squeeze, shoehorn in this little space, and it's a stainless steel, but it's got all this coloration. This was in a fab yard, and they were shot blasting, little small beads, and those beads, carbon, contaminated, got spread all over the place and contaminated the stainless steel. So it's just localized pitting, and that's. Make sure your stainless steel has a coating on it, a little coating on it, or preservation. Make sure it's covered during fabrication. All right, system design. What are some general rules? Simple, keep it simple. High heat rejection. You'd be surprised at how much heat rejection. You get a variable speed drive. Some of these big compressors, they kick out a ridiculous amount of heat. High reliable equipment, high in reliability. Innovation is great, but you got to be careful. Access, you got to pay attention to access. Straightforward sequences, this isn't, VAV systems are not used. We have some horror stories about those. System redundancy N+1, local exhaust ventilation, ACGIH, industrial hygienists, good stuff, capture hoods. We deal with lighter and heavier than air gas, so you may have a module, one exhaust up here, exhaust down here. Battery rooms are a good example of some of that. Building envelope impacts. Pressurization and leak testing, blower doors. Good way to test your module for leakage. And when you get into safety scenarios of a temporary refuge, that's very important. So temporary refuge, it's a space or a building somewhere where guys can go when it upset conditions, catastrophic events. Temporary refuge, usually it's based on a specific endurance period and maximum allowable temperature. You can have communication equipment, process control equipment, so you can orderly shut down your operations in there. So it's kind of like a panic room, or people come in. We would muster in this room, temporary refuge, but in this corner there'd be enough process controls so we can still see what's going on and try to shut things down. Requirements for HVAC. Thermal radiation, just temperature. We have a fire blazing down on us. How hot is it going to get? And then we look at coatings on the walls and fire dampers. Breathable air, how much O2? Is there enough air and oxygen in the air? Are we going to breathe it all up? And then on the flip side, carbon dioxide, how much are we emitting? And there's a lot of studies, and as the anxiety rises, oxygen depletion goes up and carbon dioxide goes up. All right, so an example would be a temporary refuge designed for 60-minute hydrocarbon jet fire, max internal temp of 104. That's pretty hot. And I think, if I remember right, it's like 104, 98F, something right in there. That's when you start saying you start making bad decisions. So, if there's a fire outside, I guess this is where it gets to safety. If there's a fire outside, we want to make darn sure that PR is protecting our guys. And this gets really difficult. This is some of the hardest stuff to figure out, because where's the cooling come from? Where's the fresh air come from? Really challenging. This is a living quarters with the heli deck. It's being lifted. Must be being placed on a platform. This is actually a North Sea asset. It's 1, 2, 3, 4, 5, 6, 6-story living quarters. Like 200 people live in there. Okay, intakes. Kind of basic stuff. Graded, separation distances. The big two: the gas dispersion analysis and the exhaust dispersion analysis. That's really the only way to figure out where to put these things accurately. Do estimations, but if we don't have a gas dispersion analysis, we don't really know how our gas is going to move. And then particularly on larger greenfield, new build stuff, the exhaust dispersion, if we have power generation here, or helicopter approach, or plumbing expel, not plumbing quite, to figure out where the gas turbine engine generators, emergency generators, you don't want to suck that in. That's happened more than once. Once a week they got to shut off the HVAC because they're testing the emergency generator. That doesn't make people happy. All right, try to speed it up here. Yeah, I saw me roll on. Okay, fire and gas. Dampers, internal dampers, a lot just building industry, UL 555, external dampers, onshore. We don't really use those much unless it's a temporary refuge. Offshore, always for occupied facilities. Gas dampers, if we're in a hazardous area, this unclassified building in a hazardous area, we always use them. Offshore, they're pretty much used everywhere, just good practice. The gas damper, so there's no such thing as a gas damper. You can't go to a vendor and say, give me a gas damper. Buy a low leakage damper. And what we practice here in the US is to, at least my company's practice, is to look at UL 555S class 1 smoke damper. That's how we say our leakages. There's an equivalent ISO European applications for blast dampers, smoke dampers. Aircraft dampers are not gas dampers or isolation dampers. They are not in that application. Pressurization. 496 governs it. Key points are: you got to maintain 0.1 inch or 25 pascal positive pressure, 60 feet a minute outward velocity through all the openings. If the system fails, it has to be alarmed. So that is then our control room, our electrical room that's in a hazardous area. We got to make sure it's positive pressure. Open the doors, guys walk in and out. We have outward velocity. Use of vestibules and airlocks, best practice. We don't see that as much as we'd like to. Base is usually what kills it, but that would be the best. All right. Pressurization that we typically see facilities. Here's some facility types unclassified on the top. Location hazardous, and here's some related pressures: 0.1 inch and alarm monitoring. Interesting piece here, getting back to the blower door test, is the integrity. How do you check it? How do you know you're have this pressurization or this tightness of your building? So we would do a blower door test to prove, for the top example, 0.25 air changes an hour, and we would test it at a 0.2 inch water column. It's just an envelope integrity test, really. About it, design deliverables, normal stuff that we all see. What I want to point out is procurement requirements can get crazy in oil and gas. Yeah, those can really bog a person down. B&IDs, super important. They're not your standard building services. FATs, very important. You do type testing where you do like 10% of your units, or you can do all of them. And they go offshore or remote locations. If you only type test 10%, you find out you have failures, that's a bad deal. And commissioning and air balancing. Common things we run across, design capacity is insufficient. Not quality D&IDs, vendor fabrication not meeting specs, FAT not meeting design. The problems we run into. And I'm going to leave you and hand over to Mac, but this is what a typical ID looks like with an air handling unit and flow paths and instrumentation on it, so forth. So that's my background. Now Mac's going to get the details. All right, let me use this. This was not a bow tie, it's a microphone trick.
All right, so we'll get into the application side of the stuff there, just going through, talk quickly about construction limitations, really for, this is based mostly on North Slope application. Safety design applications, facility siting as it relates to our practice, energy efficiency considerations. Some things to be considerate of if you're doing a project on the North Slope are seasonal constraints. One approach to this would be your district heating glycol tie-ins. You obviously wouldn't want to break down your whole heating system dead of winter, so really limited in how we can deal with that. Environmental concerns can be a huge deal. You have a migratory bird on the way, and if you stop a project for months. Had a polar bear den down in the well house just months ago. That was a big stir up on the slope. A lot of regulatory requirements put on us, federal and state spill response perspectives and permitting. Logistics is a huge deal for the North Slope. We'll talk about that some more. I'm working on a couple projects right now that are ice road dependent, which puts a whole nother spin on things because there's a really short, narrow window and you can get all your materials over to the job site to get your work done. Have worry about your personnel safety exposure in the harsh Arctic environment. Cost of field labor is extremely high, so we do try to bring all of the field work we can into a fab shop, Anchorage or out of state, truck everything up, parse things up that's needed. Really, the goal is fast tie-ins for efficient project delivery. Project delays can cost millions of dollars. So my story on this is a project I was working on. We were having actuator issues. And project lead called me up one day and told me if we didn't have it resolved, we're looking at $1 million a day in production loss. Basically, the actuator problem wasn't going to be acceptable. Really don't want to have those phone calls. So that's part of what Eric's talking about, is having a real detailed design and plan really in place so you don't run into those gotchas at the end. Getting into kind of the logistics side of things, I think most of us know this up here, but the two transportation methods we typically see be a sea lift module, which is up there on the left. That's a manifold module up park. And On the right is a truck module, which is more common recently. That's a blast resistant control room, which is kind of, I wouldn't say it was a temporary refuge, but it's a control room made to keep you safe for a short duration. The coating over the an intimescent coating over the outside for jet fire exposure. And use special hydrocarbon pyrodampers and things of that nature. So we have limitations on what we can do with the truck module size. Typically, we'll see a 60 foot by 20 foot, 65 foot by 20 foot size module. Occasionally, we'll get into a bigger one, which is an 80 foot by 20 foot by 15.5 foot tall. Really, the height is driven by bridge heights on its way up to the north slope. Cozad trailer, that's a picture of the Cozad here. It's hard to tell, the truck's here, and it ends way over here. It's really massive and costs, I think, 150 grand extra round trip. And the C-lift module, obviously we have a lot more flexibility. The real work comes in once you actually get it large enough to truck dock, and they have to get it on rollers and slowly move it into place. Haven't done one of these in a long time from our company's perspective, but E&I recently. Why do we care about that from our HVAC design perspective? Eric mentioned our designs basically made based around the module volume. We generally have the largest piece of equipment in the space. This is the pigging another pigging module. Outline the air handling unit here. It works. We barely got all the clearances for the NEC working clearances, gaining access to your filters or your motors. But it's pretty shoehorned in there. It's important for us as the HVAC engineers on projects to try to allocate space early in the project. It's hard because a lot of times they don't bring the HVAC engineers in until after the first initial FEL 1 or FEL 2 phases. They bring you in at the last minute after the process design is almost complete. That should be the first goal, is to make room for that large piece of equipment if you come onto the oil and gas facility. Ask for extra space because things tend to grow as design progresses. Throw in some Arctic design considerations. Arctic tees really have proven to be less effective than originally premised. As you can see, collecting a bunch of snow and adding more snow loading onto the structure, and they've had to add different additional support for these. Really, all we're really seeing anymore is 90-degree downturn hoods. That would be my recommendation moving forward. So then we get into the actual equipment selection for these hazardous locations, that classified areas that Eric was talking about. We need to make sure that our equipment is listed and labeled by a U.S. NERDL if we're working in the United States. So UL, CSA, US, Intertech, there's a lot of options there, but we want to have a listing for your devices. Explosion proof is generally preferred over intrinsically safe equipment. I say this because I've done some intrinsically safe equipment stuff, and there's a lot of requirements that go into it with the wiring, tagging, and coloring, and most people don't know how to build them correctly, and it becomes kind of a problem once your QA inspectors go down there and start pointing out all the problems. I think I had about $30,000 refund at one point because it's that hard for them to build it that way. And one other note I'll just throw out here is if your HVAC system is being controlled by your fire gas control system, you may need to get your devices listed for use with the control system. Something to just flag. Doesn't always work that way, but motor selection considerations. One thing that we hear a lot is Arctic duty motors, and when is it right for those? Really, the way I typically approach it is if it's downstream of a mixing box or a heating coil, wouldn't use Wouldn't use an RF duty motor. Really, when you run into trouble is going to be your start stop of your motor. Hold start, fail if it's not, if it doesn't have the appropriate pedigree. But if it's 100% outside of your unit, it's definitely going to see that minus 50F or minus 60F outdoor air temperature. Definitely. One thing that comes up occasionally is if a totally enclosed fan cooled motor is sufficient for Class 1 Division 2 areas, or do you have to do the explosion proof motor? That kind of depends. So a lot of times you'll receive a TEFC motor, but it won't say that it's suitable for Class 1 Div 2 Group D areas, Group D methane. So then we end up sending the motor back and getting a new one. And ultimately, about 3/4 of the time, I've seen it just get changed out for an explosion. So it's something to be wary of as you're doing your design. A lot of these motors for these hazardous areas will come with over temperature switches or clicks-on switches. Really what they're doing is they're keeping your motor safe and at a T code or a temperature code below the auto ignition temperature of whatever your hazard is. So that being methane, we typically pick a T3 temperature code, keep it below 200 degrees C. Why do we need to confirm whether the motors we're getting from our air handling unit supplier or our pump supplier, if they're coming with these clicks-on or over temperature switches or not? There's a lot of confusion, especially with air handling units, where we'll still get, even though we're putting something in, let's say, a ream, an unclassified module or a control room, and we don't want the over temperature protection. A lot of our vendors won't know the difference because we're doing process modules alongside our non-process modules, and then we'll end up with a motor with clicks-on switches on it, and then it has to be wired in, but nowhere to land the wires. Problem with people. Nobody's very happy with you when that happens, so it's just something I'll throw out there as you're selecting your motor for your application. Make sure your middles show the appropriate items. Then we get into fan selection. Selected our motor. Now we have different spark resistant construction types for different fans. A type A spark is constructed of all non-ferrous materials, kind of the safest option. Also not a very common one, and they find an expensive approach. Type B spark is the impeller is constructed of a non-ferrous material and is assembled to reduce likelihood of contact between moving and stationary parts. And type C spark just requires us to reduce contact likelihood. I've generally seen type B spark used throughout the industry. Definitely something to be aware of as we're selecting these fans. And we have our actuators. This will be dependent on your client and what your situation is, if you have an instrument air system or not. So kind of the original standard when I came into this side of the industry was we put a general purpose actuator in this big explosion-proof box, and then mount it to the side of air handling unit or damper or whatever that may be. Fairly recently, I don't know, probably in the past 6 or 7 years, we've shifted into doing more of these self-contained explosion-proof actuators. These are electric. Pneumatic is still really common in the big central processing facilities or gathering centers. Be good enough. Put some, so you're aware of the options that are typically used. Amazing how heavy those ones in the middle really are. They don't look that bad. A ton. Most operators will utilize, many operators, I would say most, but will typically utilize their own process PDITs and RTDs and pressure differentials and temperature devices. So what I've shown there is kind of what was this. These are typically used for process conditions, but because of the way we stock things on the slope and what our instrument techs are used to working on, bringing in HVAC specific devices is not something that's accepted by the instrument engineers on projects. There are some specific HVAC devices available though that are explosion proof. I just haven't seen. I guess kind of working through, wanted to just run through kind of an example. Let's say we have an H2 occupancy, a hazardous occupancy field gas conditioning mod. We're utilizing the adequate ventilation that Erik talked about to help reduce the hazardous electrical area classification. We're going with the standard 20 foot by 60 foot by 13.5 foot wide high truck mod, and electric heat is required. We don't have any glycol heat. So kind of just two typical ventilating options that we discussed would be to get adequate ventilation to reduce our hazardous electrical area class would be to do 6 air changes per hour, kind of like API RP 500 or 505 is pointing us to. But also with 100% outside air, or you can look into the recirculating air option that Erik discussed, where we have gas detection and monitoring continuously, where we do 4 air changes per hour with the ability to increase ventilation to an emergency ventilation rate on gas detection. So option 1 obviously would require an explosion-proof electric heating coil in the air handling unit. Bring in 100% outside air. We're going to have to heat it somehow. Option 2 allows us to use recirculated return air to temper the incoming outside airstream. So no heating coil is really required. Heating can be picked up by remote electric unit heaters in space to avoid really big explosion-proof electric heating coil in your air handling unit. So looking into option 1, the air handling unit size came out to 17.5 feet long by 30 inches by 30 inches to provide 1,000 CFM of tempered outside air. The explosion-proof electric heating coil is really what's driving that 17.5 feet long with the 3 to 4 feet clear upstream, downstream requirement for those. So the below example is a real example. It's an outline. Also, I should note, the AHU did require summer and winter filter sections on either side of the heating coil, so making it even larger. You don't want to have the filter upstream of the heating coil frost up in the winter, but we also don't want to have a bunch of dirt and dust and debris come into the heating coil during the summer months. So you have to swap the filters out basically on a 6-month cycle. So in this example, we had to build a separate structure on the side of the module just for the air handling unit itself. And you can see how it kind of shoehorned in here with the structure. You don't really have great access to the control panel or anything in this example. And you're required to heat the full 6 air changes per hour of minus 50 degree air. Move to the option 2 one, which is my preferred option, where we have a little smaller air handling unit. It's just 9 foot by 61 inches by 34 inches, provides you 1,000 CFM outside air. The air handling unit fits in the truck module footprint. This is the air handling unit here. You do require separate electric unit heaters, so you do have space considerations for these and your NEC working clearances to the connections. But you're only required to heat 4 air changes per hour, minus 50 degree outside air. And it adds some benefit because we get your, let's say, a 40 degree discharge air temperature at minus 50, you're going to get roughly 12 air changes per hour. The unit's going to be roughly the size for 12 air changes per hour. And 4 recirculating and 8 recirculating and 4 coming in.
So is the 1,000 CFM, is that based on the 12 air changes, the 1,000?
The 1,000 in this example is based on the 4.
Okay.
So that they're like,
But the total air
they're
handler is,
like examples. So your total airflow coming through this module is twice what the airflow would be in the other module. So it allows you to add some additional cooling capacity in the summer.
so it's a 3,000 CFM unit.
And then it also allows you to bring in emergency ventilation rate on gas detection. provides a little additional layer of protection. Then we have to worry about the relief and exhaust air requirements. We need to know, and Eric mentioned this, heavier or lighter than air vapors or both, propanes or methanes. One thing that we like to do, I just showed an example of an option you could do for a short module. I wouldn't recommend this for a sea-lift module because the stack effect is actually pretty impressive on anything that's probably over 12 feet. 20 feet, sorry. That's Nathan Ziegler and I did some work on that a few years ago where the lower reliefs became intakes. Bringing all the outside air in and everything was exhausting out the top. We ended up having to swap those out for mechanical modules, exhaust fans in, which sounds easy, but it's not really with all the oil and gas effects. Better design it right the first time. I do recommend keeping the module slightly positive in pressure just to keep infiltration down, even if it is a process module, depending on how close it is to any other spaces. So if it is actually attached to another space, there's may not be able to. So HVAC control system selection in the oil and gas world, kind of do a full gamut of options. You know, a lot of our older stuff is in the basic process control system. We do have some SIS systems we get tied into, and some operators do use the fire and gas control system to integrate with the HVAC system because they are kind of linked with the gas detection actions. And talking through that, some example actions could be something that, oh, yeah.
Can you go back a couple slides and speak to, I think this, are those dampers in there on the inside?
Manual dampers? Yeah, just volume dampers.
Yeah, okay.
Those are just volume dampers so you can dial it in and balancing
Okay,
so that you don't stick all your air on the top.
yep, okay, I see. Thank you.
It's not really elegant, but we do like to keep things simple.
Yes.
So, process area gas actions, emergency ventilation start. This is just an example of what you could do. Different operators will have different guidance on what they like to see. Say we hit a 10% LEL on a gas detection system, that can start our emergency ventilation rate on that larger unit we were looking at. Until the gas condition clears plus an additional 15 minutes. And then if that doesn't work, we're going to go to our high gas alarm, and that's where it's going to go to the board operator. We'll set off the beacon lights, and the evacuation of the needed area. If we keep going up to that 50% LEL, that's when the facility and pad evacuations could begin. Have gas inerting systems, those can be activated. One thing to note is with some gas inerting systems, they require the space to still be warm when they actually release. And it's just something we've been working through recently on our end. So otherwise it's going to be a puddle on the floor if you.
So like Halon Novak you mean, or you mean?
Halon's okay. It's really the Novak. 1230. You want, ideally you'd have the room be about 70 degrees when you release, because it's going to drop the temperature in that module immediately. But found that from some of our studies that if it's not warm in there, it's just going to puddle on the floor. So something to consider. And then if it's a non-process area or an unclassified area, you know, we hit that 10% LEL, probably at a gas detector at the discharge of the air handling unit, and shut the ventilation down and close it down. There shouldn't be any gas in the space causing the LEL. It should be coming from outside. And kind of to add on to Eric's note, gas dampers must be driven close to both process and non-process areas to protect the space, meaning no backdraft dampers. They don't work that well in the Arctic anyway. So another Arctic design consideration, size your intake hoods to have maximum face velocity of 500 feet per minute at your emergency ventilation rate. I get asked a lot, why do we use, we're only bringing in 4 air changes per hour, why don't we size our hoods for just that instead of the full ventilation rate? The reason is because in the summer, when we go to cooling, we are oversized or undersized. Those are all mosquitoes. We're gonna pull all sorts of crap in here. Filters. Facility siting. Let's touch on this briefly. Why it's a big deal to us is really, this came to light in the 2005 Texas City incident, and OSHA's really heavy on it now. During this incident, I think it was 15 people died, and it was mainly related to people in a little office structure near the blast site. The office structure wasn't rated for the overpressure event, and they were crushed by the building. Camps and control rooms or unclassified areas or areas where you have high personnel hanging out, you need to consider where you're putting your building in relation to potential overpressure scenarios. So what's shown here is the CPF1 control room module. So that's blast resistant module. I think it's 8 PSI blast. And you can see that skin I was telling you about on the trunk module, the intumescent skin. It looks a little different than the other buildings. So we get into penetrations in these types of structures. You have to use a whole different type of penetration scheme. Really, I'm just kind of pointing this out to you guys. If you ever do a blast resistant control room or something on a platform of this nature, the J ratings on the building skin, get into making sure that the plumbing vents, the fire water penetrations, and all of those have the appropriate material that'll close in the case of a jet fire, so that it doesn't come through the wall or the space. And our two primary exposures are the overpressure exposure and the jet fire exposure, generally, that I deal with. So all buildings have exterior openings. And our blast dampers, and each 120 fire damper. So that's for a hydrocarbon fire for 120 minutes. That's theoretically rated for. Not common, but very interesting. Then Eric touched on this with his temporary refuge, but you got to understand if you're putting people in these buildings, what is the plan to get them out? Is it a shelter-in-place facility? Are they just supposed to take the initial event and leave immediately? Closing these buildings completely up and protecting the occupants. How much oxygen do they have? How are we going to deal with something like this happens? Just a good question to ask in these types of scenarios. 1 in 33. This happens all the time. We put quarter-inch or half-inch. It's always frosting up. This one is actually in the Tyomic platform. I like this. Is the wastewater treatment plant. They got tired of it frosting up, but they couldn't get to it. Put a brush and had 3 different broom handles duct together. And they come out of the camp, scrub it in the morning every day. So really quickly, energy efficiency consideration. Sounds weird in the oil and gas industry, but we are actually getting heavier into our greenhouse gas emissions concerns, especially with carbon tax in the future. Becoming a bigger issue. One thing we currently do is on our turbine generators, we have HRUs, heat recovery units, pull the processed glycol off of those. And actually that heats a lot of our camps and office areas at the main facilities. On the drill sites, we have production heaters or line heaters because we have to keep the oil going down the pipeline, keep it above its waxing temperature. So those generally have a glycol bath on them. Those are a little lower pressure and temperature than the HRU systems, more of a typical commercial type glycol pressure, but we can use those. We aren't using those as much as we used to. It's a lot more expensive to put in all the glycol piping throughout the drill sites than it is to put electric heat in. But it's an option. It's something to be considered during the early design phases. One thing I'll note with the HRUs, at least at our facilities, that heating glycol is coming off at a higher pressure and temperature than standard commercial system. That always becomes a problem during your design phase. Special coils, special valves, class 300 system. So HVAC to hoods as high as possible. So snow drifting, yeah, you recognize this, Doug?
Yeah.
No, that's not the replacement.
But it still drifts the same.
Snow drifts are a real thing up there.
You can walk right up on it on Snowdrift.
And then just touch on some other industrial-related hazards to think about during your design if you're doing an HVAC project. Nitrogen was mentioned. Nitrogen can be a problem if we have a nitrogen generation system that's piped throughout a whole plant. To release your nitrogen, trying to fight it with air, and air is 78% nitrogen, so it takes a lot of air to keep it in the proper OSHA threshold for, I think it's 19.5% oxygen. And through the calculation you can use to determine that there. It's not a fun one, but we have a spreadsheet that does it for us now. Noise exposures, another big one. OSHA sets those allowable noise exposures for 8-hour workdays. The 82 decibels is allowed for your 8-hour workday. And explosion-proof electric unit heaters are louder than this a lot of the time, especially if you get into 25 or 30 kW models. Something to be considerate of. It's not awesome when the HVAC equipment is what's causing hearing protection requirements in your buildings. Really, you'll see that the two thresholds are 82 and 100 decibels, requires double hearing protection. That's what's driving that when you're in facilities. And these are just references. So I think that's about it. Do you have any questions for me or Eric or?
Talked a lot air side and electric coils. What have you seen as far as boilers? Any lessons learned there that?
I see a lot of boilers.
Okay.
Fire equipment's not common.
Iuga heater.
Yeah, we do those all the time.
Yeah, no, you don't, yeah. I've never seen a gas fired boiler. I've never seen a boiler.
Well, it can be electric boilers. It
You
could
could do
be
electric.
Hot water heater, maybe, but
well fired.
into those.
I call it electric heat.
Typically,
Even the water heaters are usually heat exchangers. In camp, you've got basically free
Heat available. Right.
available.
We're putting in a, say, gas fired boiler or boiler plants. You just need to make sure you put it in the gas you're providing it, rubbed and cleaned. That's the problem up there. We're pulling all of this off the lift gas line. Abundance of fuel gas up there. Not necessarily clean and ready to just put into any appliance.
Also not odorized either.
There's that too.
It's naturally harder. Do you see shorter life durations on equipment? I know some of the equipment I've seen up on the slope is, the facilities have a real high volume, mechanical equipment or HVAC, high in the space, compressor, other industrial equipment that's producing a lot of heat. So when you get up to your HVAC equipment, feels like it's over 100 degrees.
Yeah.
How does that affect?
I don't think I'd say that I've seen it, but some experience. Problem, because a lot of that stuff parts,
Okay.
those high spaces like you're talking about, they do make regular maintenance. Not replaceable, so
Put high temp grease in and call it good.
I guess.
Thank you.
A couple of quick